So we do these sequentially. So first we do these red ones, and then we do the orange ones, then the green ones, then the blue ones. And the order is here chosen such that no ancilla is ever involved in two entangling gates at once. No code qubit is ever involved in two entangling gates at once. And when an error happens on an ancilla and gets spread to the code by the action of the entangling gates, it does not cause the single qubit error to become a two qubit error and mess everything up. At least not, yeah. So it does it in the direction that doesn't matter, at least. If you want more details about that, it's in the small paper. Once we've done all of those, so you might notice that the red and blue, well, we don't have the red and blue colouring on here, but there's a different order here and there to achieve that. So what this means is we do these 4 rounds of entangling gates. So we do 24 entangling gates overall, and then we have to measure the ancillas. So there's 8 ancillas to measure. So we do these 8 measurements, and that's the syndrome measurement. We do 24 entangling gates, 8 measurements, then 24 entangling gates, and 8 measurements, then 24 entangling gates, and 8 measurements, and so on until infinity. And the time it takes for a round is the time it takes to do those 4 entangling gates, well, those 4 rounds of entangling gates and the measurement. The way to initialize this code is quite easy. We'll talk about it for this choice of stabilizers because that makes it a little bit easier. The logical Z is just a chain of 3 Zs from top to bottom. So Z, 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 or Z, Z, Z. So if you want to be in the 0 logical state, you want to be in the +1 eigenstate of the logical Z. And one way you can achieve that is just to have everything in a +1 eigenstate of Z. So have all of your code qubits in state 0. Then you will also be in a +1 eigenstate of these stabilizers, which is nice because you're at least halfway to the stabilizer space, but you're not in an eigenstate of these stabilizers. So if you prepare everything in this product state and then measure the syndrome, these are going to give you completely random results. You're going to end up in a highly entangled state, because it's going to be an mutual eigenstate of all of the stabilizers, but these are just going to give you random results. And so random that if you try to do error correction, you would get a logical Z error half the time, but no one cares because you're preparing a logical Z eigenstate, so the logical Z error doesn't do anything. So you have successfully prepared a logical 0 state of your code by first putting it in a product state and then doing a stabilizer measurement. Similarly for logical 1, logical plus, logical minus. If you want to do readout, you just do this sort of backwards. You start with a state. If you want to measure logical Z, you can measure Z everywhere, and then you can take this as your logical Z. Look over here, see how many 1s you have. If it's even, then you have logical 0. If it's 1, you have logical 1. But maybe a measurement error happened, maybe some physical errors happened. To work that out, you can also reconstruct these Z stabilizers to tell you something about the errors that happened. They'll tell you about the bit flips. The bit flips are the ones that are dangerous to your logical readout, so they can help you work out if something went wrong. You won't be able to extract information about these, but they tell you about phase flips, and you don't care about phase flips anymore. So you just measure everything in the computational basis to readout and the computational basis. So then the simplest example of an experiment would just simply be, if you want to say, prepare in the 0 state and read out in the computational basis state, you would prepare everything 0, ancillas and code qubits. You would do the entangling gates, and then finally you would measure, where you'd measure the ancilla qubits to finish off the preparation, because they need this syndrome measurement, and then you would do the measurement of the code qubits to do the readout. But the nice thing about the last layer of syndrome measurement is that you can do these two sets of measurements at the same time. You can do the ancilla measurements at the same time as you do the code measurements. So effectively then, you don't have to wait the amount of time that it takes to do the measurements of the ancilla before you start the readout, which saves you a bit of time and will make this first layer, this phase 2 experiment, as I call it, significantly easier than when you go on to the phase 3 ones. So it's just prepare, gates, measure. Well, I say just. It's just taking 17 qubits and preparing them all in the 0 state, and then doing 4 rounds of nicely addressed high fidelity entangling gates, and then reading them all out. Easy, huh? So this is our code. We prepare, and then sometime later, which is given by the amount of time it took to do these gates, we read out. So what is our benchmark? What does this have to beat in order to show, yeah, quantum error correction does stuff? Well, we could, so this is made up of physical qubits. Let's assume that they're all the same type of physical qubit. These are all quantum dots or whatever. What we could do is take exactly the same species of qubit and just initialize that in the 0 state while we're doing our experiment. So we do our experiment, we've got our code here, we've got our single physical qubit here. There's no difference between this physical qubit and the ones that make up this code. And we prepare them all in the 0 state. Then over here we do our entangling gates. Over here we do nothing. And then we measure everything. And then we take the data from over here and say, what is the probability that the 0 state that we prepared is what we read out? And then similarly over here, we look at the probability that the 0 state we prepared is the one we read out. And we see if this highly complicated 17-qubit entangling gate, blah, 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 code actually stored it more faithfully than just a single physical qubit. And if it does, then finally we have shown that codes are greater than the sum of their parts, and we can continue on until quantum computation and beating cryptography and stealing from banks and being rich. Because no one's invested. Yep.
Success measure is not really whether it's longer, whether it's better. It depends on the relative gate time of the new logical qubit.
Yeah.
I know they take this as a measure of success. You know, you
Yeah.
can say, well, I make a qubit that's longer, but the gate time is 10 times longer.
Mm-hmm. Yeah, so it's going to depend.
Does that mean that, okay?
Yeah, I'll touch on that a little bit later, I think. So, yeah, at least this is a situation where we can say whether one thing is better than the other, although the amount of time we wait for this thing depends on the other things, so they're not entirely independent, but what can we do? Well, one thing we have to do is decoding. So decoding is what we do in the readout step. We measure all of the Zs, we get the syndrome on the white plaquettes if we're doing a computational basis measurement, and we also get our logical Z. And we have to ask, this logical Z that I've been given, is it telling the truth or is it lying? So we can look at the syndrome to get an idea of that. So say that all of our syndromes come out +1, so everything's saying everything's okay, except that one. So this means that highly likely there was a bit flip here. So if we're using these three as our logical Z, we measured these three, we counted the number of ones, we see if it's odd or even, and we get our logical readout from that. Then we can say it's telling the truth. We don't have to change it. We will trust it. Whereas if we use these three as our logical readout, then we would see, okay, most likely there was a bit flip on that one, so it's lying. We just flip the value, and all is well with the world. So more complicatedly, we have to look at the whole syndrome, what's going on all of these, and work out, is it more probable that our logical operator is telling the truth, or is it more probable that it's telling a lie? So typically, we will use a fancy algorithm for this. So as Barbara was talking about earlier, for a larger, an arbitrarily large version of this code, we can use all kinds of stuff. But in this case, we don't have to use any fanciness at all. we can be completely unfancy because there are only 8 binary stabilizers. So the syndrome is always specified by an 8-bit string, and there are only 256 possible 8-bit strings. 256 isn't actually a big number. So we can actually run loads of samples in which we simulate noise, work out what syndrome we get out, do that loads of times so that each syndrome gets a good number of samples each, and work out the probabilities for each syndrome that the logical operator is trustworthy and the probability that it's lying. And then when we actually run the experiment, because when we're doing that simulation, we've put it in a definite state. We know what it was, we know what it read it out as, so we can see if it's telling the truth or lying. And then when we actually run the experiment, we can just see what syndrome we get, look at the trustworthiness probabilities, and see whether we should flip or not. So this is a great decoder. This is the best decoder ever. It does absolutely maximal decoding. Nothing could ever be better. And you don't even have to make any assumptions about the noise model. You don't have to know anything at all because you just get this experimental data and work out a bunch of probabilities. So if I want to run this, then it only takes a few mayfly years to run. It's really fast. Yep.
You think you need any assumptions?
Mm-hmm.
You're simulating the noise, don't you model the noise?
Okay, yeah. So if I was in the lab and I wanted to do this experiment, I wouldn't need any assumptions when I'm doing my decoding. But when I'm not in the lab and I'm simulating the lab, I have to make assumptions about the lab.
You work out your additional probabilities from experimental data rather than simulation.
Yeah, you would be able to do that. Yeah, so that's the great thing about this. But of course here... pardon?
So I don't understand.
Well, you always know if a logical error has happened because it's a situation where you put it in the state 0 and then you read it out. Or even in the lab, you know what you're preparing it and you know how you're reading it out. So it's all... Yeah, I mean, it's all supposed to be telling you scalability for this case where you don't know what it's going to read out as because you did a load of gates, but we're not doing that. Yeah, so this is our decoder. We can't really call it our decoder because it's nature's decoder, it's mathematics decoder. I didn't spend any of my creativity tweaking parameters in this. But where I did maybe tweak parameters a little bit is the noise model. So we have to look at noise on everything. So, yep. When we prepare states, we have to account for the fact that we might have prepared it wrong, and we just say that if we prepared 0, there's some probability that actually we prepared 1. Measurement noise, there's some probability that it lies. And then we have decoherence. We just take the same error model as in the Tometer and Swore paper, so it's characterized by T1 and T2 times. So the T1 time is the time scale for bit flips, and the T2 time is the time scale for phase flips. And in perfect entangling gates, we depart far from anything that's physically relevant by just saying depolarizing noise. That's something that's bad. Let's use that. So we use depolarizing noise for that. And then the fidelity for our benchmark qubit is just the probability that a preparation error happened, then the probability that a bit flip happened during decoding, then the probability that a measurement, so that should be an M there, a measurement error happened. That's approximately because I've left out all of the factors of other things not happening. And to find the corresponding fidelity for the code, we have to do numerics. So I state the numbers in terms of fidelities for these to be a bit more experimentally accessible. So to talk to the experimentalists a bit more. But my fidelities are probabilities that bad stuff didn't happen, which you can do when you're just throwing Paulis at things. Of course, they can't do that, so I'll need to have another section in the paper, perhaps in a next version, which has a translation section for experimentalists talking in terms of better things. But yeah, we have the fidelity for the entangling gate is the probability that depolarizing noise happens on neither qubit. and then for the other it's just 1 minus p. For the decoherence time, we don't actually care what T1 and T2 are, we just care about the relationship between them. So T1 over T2 characterizes how common bit flip errors are in comparison to phase flip errors and vice versa. And then the time for the gates over T2 will give us explicitly what the probability for our bit flip and phase flips are.